Thank you, Marco. Good morning, everyone. My name is Monica Campos. I've been working in PM materials for too many years ago. I am not going to count it. No, it's better. Some details is better to put it in. Okay. And today my talk is related with post-sintering treatment. Post-sintering treatment is a big group of finishing operation that we can apply when we need to change something from our PM component in the asintered state. When we have the final component after the furnace, maybe we want to modify the shape, we need to adjust the geometry, or we need to change the microstructure. This group of supplementary operations can be divided in two main groups. Those related to the geometry, dimensions, and tolerance can be repressing, coining, sizing, machining, or joining different parts. And the other group are related to those treatments that modify the microstructure, that affect the chemical composition, because maybe we can do a surface treatment to enrich the chemistry of the surface and then modify the final performance of our PM component. We need to take into account that in PM material there are two main aspects that are affecting this group of... I will try to be there. Okay, there are two main aspects that are affecting this supplementary operation because we are working with PM materials. One, of course, is the porosity. If something is wrong, blame on the porosity, because normally is the guilty of this system. And also, we have to deal with some heterogeneous microstructure. In case, for instance, of machining, when we have a heterogeneous microstructure, these alloying elements can affect the local hardness of our component. And machining, you have to take the idea that if we want to machine a PM component, our cutting tool is going to see a pore material is just is not a continuous process. And then when we face with the material, it's not continuous, the hardness. There all the time the cutting tool is going to see an heterogeneous media. That's why it's the reason how machinability of the PM system is not as easier, well, it's not easier in any case, but it's more difficult than in conventional metals. In secondary operation related to the composition, of course, heterogeneous microstructure determines the hardenability of our system. And porosity. Porosity lowers the tool life. That's the reason why we need to include some additives that make it easier, the machining process. Can trap some electroplating solution, maybe that we need for cleaning our component, or retains the oil that we need for lubrication. If we retain some liquid and is working our component, we increase the pressure into the liquid and then they can form an internal crack in the component. Then it's possible a reason for a further fail of when it's working in the system. If we consider the porosity, related to the properties that we have when we want to determine the microstructure, the powers always lower the strength, the hardness, the ductility, the toughness, etc., etc. But also lowers the heat transport. That means that we are going to decrease the ability of this component to form martensitic microstructure or binitic microstructure, because we have like insulators inside our microstructure. Therefore, we need to know how is the porosity, how big it is, where it is located, if it's well connected or is isolated, because too many properties depends on how is this pore skeleton that is around our sinter body. Let's start with those secondary operations that are related to geometry, dimension, and tolerance. And the first one is repressing, coining, and sizing. Maybe we have in mind that the conventional PM route is put the powder into the mixer, then go to press, and then sinter. But in some cases, then we took the component and put back again into the press. Why? Why we need to put again a part into the press? Because this is a difficult step. We are going to put again a or final form with a relatively high level of hardness, with a relatively high yield strength, and then press it again. What reason we have to do this? We want maybe to increase the density, or maybe we want to calibrate the size, or just we need to coin the surface, maybe to print a logo, or to print a test, because our supplier need, our customer need this kind of identification in our component. But even if all of them means plastic deformation, the level of the plastic deformation is quite different. It's not the same to try to increase in more than 10% the density of the component than to test a logo here. Then we can divide this method to press again our component in three main groups: repressing, calibration, and sizing. For higher pressure to lower pressure, all of them requires plastic deformation, but in the case of repressing is the highest one, and then we can increase here up to 20% the density that you have achieved at the end of the sintering processes. Sizing is I think is the most frequent step that is included in the PM route, because we can adjust the tolerance. Maybe the densification that we are going to improve, the level of the densification is relatively low, because maybe we can expect 2–3% more of densification. But the point here is not to close the porosity. The point here is to adjust better the dimension of the component. Let me explain this graph. Forget it, what is printed here, okay? Is plotted the level of tolerance into with the physical properties. How we can increase the physical properties and how we can move between the tolerance that we can achieve. In this part of the graph are plot those transformation, those steps that are related with phase transformation. In this part of the graph are plot those steps that are related with cold working. When we make a state that has the final effect on the component is a cold working processes, then our level of tolerance is relatively tight. But when we try to modify the microstructure and we put into the furnace our component, we are going to increase the distortion. That's what happens when we sinter the component or heat treat the component. But we need the heat treatment. We cannot use the component just after the press machine. How we can improve then the tolerance, the level of tolerance of our component, just to compare the range of tolerance that we are moving when we consider the sintered steel. This is more or less the range that we can achieve at the end of our processes. It's very competitive if we compare with the others, of course. Those related with machining should be better than in the case of PM materials results. Let me show you here the typical tolerance of a calibrated component. This is just after calibration. Of course, not all the dimensions have the same level of tolerance, but all of them are relatively tight. And let me show you here how we can move into this range of tolerance when we choose different routes of PM process. If just mix press and sintering, then we can stay between an 80, 12 to 10 tolerance. But what happens if in that point we include the sizing? Then we move to a close tolerance level, IT9, IT7. Other possibility, higher performance, is go to a further densification. Then we can go to 2P2S, then 2 pressure, 2 sintering, press and sintering again. Okay, 2 sintering process. In that case, we move to an IT about 11.9, worse than this first that we have chosen. Then, trying to fix better the geometry of the component, we need a final calibration or a final sizing. In that case, we can move to a close level of tolerance. Of course, this component has the best performance, the best tensile strength, hardness, even ductility, because we reduce the porosity, but also has associated the highest cost, because we put 2 times this component into the furnace and put 2 times this component into a die. Well, 3 times, sorry, pressing, second pressing, and sizing. Let me show you 2 examples. This is how we can modify the tensile strength by the sizing pressure of different bronze components, bronze materials. By increasing the sizing pressure, we can increase the tensile strength. This is the same that we can see here. This is the finished part. The powder is a typical distal oil powder. And after sintering, we have this level of density. After sizing, with a 4–5% of reduction, we can increase the density to that level, and then we can increase the radial crossing strength in this amount of the component. This is a very attractive way to increase the performance without touching the chemistry of our material. This is an option that we have to increase this level of performance. What happens if we want to make this second press and sintering processes? Let me point out what happens if we have a steel. Imagine a steel, doesn't matter the composition, but we have graphite inside. We have carbon addition, okay? Then we are going to mix everything, to press. This is the final microstructure after pressing. And then we have to sinter. But to sinter, look the temperature. At lower temperature that you should expect it. What it will happen if I sinter in that first step at 11–20 or 11–50 degrees? If I sinter here at higher temperatures, carbon diffuses into our component, forms whatever, depending on the cooling rate, perlite, bainite, martensite, depending on the chemistry. And then try to take this part and press again. Well, there are some press machines that maybe are able to press it. But normally it's easier if we work with softer materials. Then in the first sintering step, it's better to control the temperature below of carbon diffusion. Carbon diffusion should be higher than 700, 750, more or less. Then it's better just to press sinter our component, then press it again, because we can in somehow reduce the cold hardening work that we have done in this step, and then our material is softer. Then here we can press it again, and finally go to the furnace in the standard conditions for a steel, 11–20 or 11–50. After that, we need to size if the component has a very complex geometry, because with these 2 steps of sintering process, the range of tolerance is relatively wide. It's not enough close. We have to consider also the volume that is occupied by the lubricant. when we mix everything, we are going to put there some waxes with a very low density, maybe it's 0.7, 0.8, but occupied a very huge volume inside of our component. This lubricant is going to burn out during the first sintering process, and then left a lot of pores that we can use it in the second pressing to increase the density of our material, because this volume is free. And then we can increase the density just taking into account this volume of the lubricant that we are not using in that component. Other option is just to think about in densification on the surface. The idea was, in a great extent, the structure and the properties of the zone within about 1 millimeter, let's say 1 millimeter, determines the performance of the component. This is the idea. And then the result is, why not just to densify this layer of the component? And then there are different methods for doing this. We can choose hot pinning, rolling, hot working, sewing. I am going to give you some ideas about the hot pinning and the rolling. The final objective is to eliminate the pore near to the surface. In hot pinning, we are going to project some shoot made of steel, ceramics, depending on the hardness of the component. Then we need to choose a proper shoot material with different pressure, and then we are going to deform plastically the surface. We are going to left there some compressive stress that can help us for impact resistance and fatigue resistance of our component, and we can increase therefore the performance. The point here is the shoot pinned surface. It's like very wavy, and this can be controlled by the dimension, the size of the shoot. But the point here is, what it will happen if I choose a ball very, very, very small. Maybe the quality of the surface is nice, but what happened with the open porosity? Open porosity can trap some of this shoot. And then we are in our material, we have there something that do not belong to our component. Then we have to take into account the size of our open porosity, the density level of our component, just try to adjust better the parameters of the shot pinning processes. Because shot pinning affects too many different properties of the component. Not only the density of the surface, also the shape because of this distortion. How is the topography? Maybe we can induce, maybe no. For sure, we are going to induce some kind of texture and orientation of different microstructure. And depending on composition, if it's heavily shot pin in our component, we can induce some transformation for plastic deformation. In case of shot pinning, the parameters depends on the device that we have, on the shot that we have selected, and also on our material. It's not the same to work with a heavily alloyed steel, or with a plate carbon steel, or an Inconel, or another material with another composition. Let me show you some of the main parameters that we can control. We can control the particle diameter of the beads, the steel or ceramic that we have, the projection velocity, the amount, the density of particles that we are projected into the surface, the projection pressure, the projection time, and the arc height, how is the distance between our work piece and the projection system. And here, well, in this work was discussed the effect of the particle size when we are working with a PN material. Let me show you an example that is written in this paper. Here is, this is the material, a pre-alloy chromium molybdenum material with 0.5 of carbon content, sinter density 7.1. This is the final microstructure. This is the microhardness that we achieved with this final microstructure. This is the porosity, the skeleton, how it looks like. This is the microstructure. And this is the densification that we can achieve after shaft pinning. A proper shaft pinning. In that area, we are going to close totally the porosity. We are going to increase the microhardness of the component. And if we close the porosity, we also are going to increase the corrosion resistance of our component. I mean, this composition is not designed for corrosion resistance. Okay, it's just a steel with some level of chromium, some level of molybdenum, of moly. But in case that we close the porosity, we are able to give to the materials a tool to protect the component against the environment. And also, after this treatment, the material is more sensitive, more reactive resistant for chemical treatment, surface treatment like case hardening or nitriding. Because in this part, we close the porosity, then we can better control the diffusion that is happening in this area. And also it's more active because we increase the amount of defect, of dislocation. Then in case that we use this kind of materials for performing a secondary chemical treatment, we need to take care about the time that is that we use for make it, because it's more active than in other situations. Here is the difference. This is the sinter surface. Just we can see the same micrograph, and this just after the shaft pinning processes. This is the open porosity, and look here how it's totally closed, this open porosity. What happens if I shaft pin in my surface extremely, I think much more than my material can absorb. And here you can see the delamination that can occur if we heavily deform by subpinning the surface. Here is evident, and you can see this delamination and cracks just in watching the component. But if you perform this section of the part, you can see perfectly how you can, in that case, is heavily deform this area and is made this kind of micro crack inside. This short pinning is not succeed. It's too much heavy, too much plastic deformation made at the same time. Other possibility is to make this densification by gear rolling. Gear rolling was introduced in 2070 in Shanghai. I think it was one of the first papers. The first machine that was this gear rolling looks like here. And here you can see how we can densify, well, I don't know if you can see it too much, but we can densify this part of the teeth in our gear. We can control the densification depth. In that case, it was about 0.5 millimeter. In that case, it was 0.2 millimeters. Depending on the pressure and the sliding distance that we put here into the gear, rolling all the time. We are going to increase the tooth bending strength. We are going to increase the pitting resistance and the rolling contact fatigue. In that case, also, we are going to increase the life of this component because normally this component has lubricant in the regular working conditions. And then if we close the porosity, the lubricant is not able to be trapped by the open porosity. Then we reduce the risk of forming internal cracks by rolling the component in the normal conditions. Then we increase the life of the component at the end. We can measure this strength, that bending strength of the tooth, after the surface densification rolling and afterwards heat treatment was performed in that case. And in that case, the level that we have, the endurance limit level, was very similar that the typical level for a road reference year, 12,000 megapascals, very high level for a PM year. Another option that we have to adjust the geometry is consider machining. Machining is a very critical step. Let me show you how can be defined the machinability of a component. The material with the best machinability is the one permitting the fastest metal removal rate with a reliable and satisfactory tool life and the surface finish. And the question here is that about 60% of the component, PM component, need some kind of machining operation. But what happened here? Because when I start with PM components, always said, is a near net shape manufacturing processes. If it is near net shape manufacturing processes, why I need it to make a machining? I don't like it. I think no one that is related with PM production wants the machining, but we need it. We need it in some cases. I'm going to explain some of these cases. It's true that this machining operation can be the 20 or more than the 20% of the total production cost. 60% of the PM components needs some machining step, and this is more than 20% of the cost. There should be a big driving force that make it necessary these machining processes. Between the reasons that we can find to machine a component, maybe we can improve the level of tolerance, maybe we need a specific surface finish, or we need to produce a complex form that is impossible to achieve if we have only the uniaxial pressing machine. We can ensure a close control of tolerance. We can improve, for instance, the axis center of the component, and also we can reduce the scatter in a large-scale production of component that we can find when we are checking for a close tolerance level. Then machining in that case is mandatory when we need to ensure a certain level of tolerance. Maybe we need to improve the roughness. And here in that table is plot the roughness depending on the process that we have selected. From here to the end, there are different machining processes of different accommodation of the surface. And of course, when we use machining, we are able to go to the lower roughness level that is possible to achieve. What happens if we need to press this kind of geometry? Or this kind of geometry? It's impossible to make it by uniaxial pressing. Therefore, we are able to press that component and then machining to achieve this final form. But machinability is not a property of one material. It's a system property. Depends on too many factors. If someone said to you, I have this component made by this kind of material, is possible for machining? Is it easy to machine in this component? Can I drill it? Can I make this hole or whatever is needed? Depends in too many different reasons. We need to take into account the surface finish, that means the quality of the final component, the productivity, that means how many times I have to invert for machining the component, and the tool life. How many cutting tools I needed for machining the component. And all of them are going to give us the idea of the cost of our step in that case. If we need to judge if our component is easy or not for machining, we need to account different criteria. We can take into account the criteria for the cutting, the workpiece, like the surface quality, the manufacturing accuracy, and so on, the tool life, the tool defect, how long we can use the same tool. And then, based on this, we can say if it's easy or not, taking into account at least 2 items of this list. The cutting tool life, or the number of holes, or the cutting speed, or if we compare with the standard steel, if it's easy or not, depending on this comparison. And based in 2 different parameters of this list, we can see if it's easy or not to machine in this component. If we want to improve these parameters, then maybe we are going to choose a better tool, or we can change the cutting speed, or maybe we can introduce some specific additive for machining PM components. Let me show you some example. This is not a PM material. This is a ductile cast iron. And here in the table is writing the hardness that is achieved in different conditions. And here you can see how it modifies the tool life and cutting speed depending on the hardness of our material. This is the harder, this is the softer. In case of the harder material, you can see how the range of the cutting speed is relatively narrow. We can move just into a very narrow ranges of speed, because if we go to farther the velocity, it's impossible to machine in the component. When it's softer, we don't have this rapid decrease that is found here. The softer material is more friendly for machining in general, for wrought steels. What happened in PL materials? In PL materials, taking in consideration the hardness, this is plot the hardness, more than 90% of ferrite. Look how decrease as well the tool life that we can expect it as we increase the hardness, and how is possible to move this curve to a higher level by increasing the density or by the addition of different additives into the microstructure. What happens if we increase the density? If we increase the density, we are going to increase at the same time the cutting tool life. Okay? In that case, well, it's a stainless steel is more friendly than maybe the low alloyed steel for cutting. And if we increase the additive, in that case, the manganese sulfide is going to coat the cutting tool when the machining process is running, and then protect the tool during the process, and then extend the tool life. That's the meaning of this kind of additive. This is the only effect, this is the only one that we can consider. We have many others, and between them, this is a study that was published some years ago, but is worth it to see the results. Here is plot what happened with the tensile strength and dimensional chains, because we don't have to forget it that our component needs a certain level of performance. What happens if I put an additive that works perfectly from the machining point of view, but reduce drastically the tensile strength? That's the case of tellurium, that's the case of sulfur. What happens if we include an additive that make a big distortion after sintering, because promote a liquid phase that make heavily the dimensional change occurs? That's the case again, the sulfur, tellurium, selenium, etc. In that picture, the best option is manganese sulfide. Manganese sulfide looks like the perfect answer. Looks like here is placed in the middle of the pores or even in the middle of the microstructure. There is this gray spot that you can see, you can detect in the microstructure and age it. What is the disadvantage? Of course, there is an influence on the dimensional chains, but one of the most disadvantages is the stain on the PM steel. Let me show you better than this. Let me show you this one. This is the same component without additive. This is with a specific additive designed to avoid this stain. And this is the same component with manganese sulfide, in that case after 1 week from the sintering processes. If you are a customer and you see this component, then you reject the component directly. No? In the microstructure, there is no effect. This is the component without the additive. This is the component with manganese sulfide, and the other specific additive designed to avoid this stain. There is no difference in the porosity. There is no difference in the microstructure. The difference is in the surface. Here is more evident the result that we can achieve if we select proper the additive for machining. Then something that works very nice for machining can decrease our properties of the component and also can affect the surface finish of our component. This is so critical to select better the additive. What happens if it's impossible to perform the whole structure and we need to join different structures to make the biggest one? Then we need to join all of them. We have 4 main possibilities: sinter bonding, sinter bracing, resistant welding, and press fit. Sinter bonding part with material that was sintered, and then we are going to round the surface, place together, and put it again into the furnace to promote the diffusion. In case of sinter bracing, we are going to select properly a brace material that melts during the sintering and preform the joint. And resistance welding, we are going to make simultaneously press and temperature in some points of the components. And in case of the press fit, we need a material with enough resistance to succeed with this step. Some of the nomenclature are relatively mixed when we look to the literature. And then we see welding, bracing, and soldering. Welding is when we are going to form a pool of melted material, melted metal. It's not very frequent on PN material because one perform the melt, the pool is solidified, and then form cracks for this contraction during the solidification. It's heavily in the materials that has a porous structure in one side and densify shown because of these welding processes. Then it's not very frequent to see welding with, in PN materials. It's more frequently to see the bracing. Bracing is we are going to use an alloy, a filler metal, that we can design according to our base material to be more compatible with the chemical composition, and then place together in the sintering furnace. It's just in one step. We are not going to increase the number of steps that we need to achieve the final structure. And soldering is like bracing but softer, because here the melting temperature is below 400 degrees. Then the resistance of this joint is lower than the resistance of the joint that we can achieve after bracing. But what is the main difference of PL materials? Because these 3 main aspects that I said before are the same in the whole family of materials: welding, bracing, soldering. And here, what is the difference? And the difference, again, is the porosity. The porosity has a different effect on the welding of the material, the joining of the PM steel, because lowers the thermal conductivity. And if it lowers the thermal conductivity, also affect to the capacity of the heat dissipation that we have in our component, and also affect to the hardenability of our component, as I said before, because it's like we have insulators in the middle of our material. Of course, also condition the thermal expansion, and then can determine the susceptibility for cracking, to cracking. Then always porosity make another level of difficulty when we are making joining processes, as well as what happened with the machinability. The pore gives us an extra value of difficulty of the processes. Resistant welding, we trap into the two electrodes our component, then the current is going to pass in that direction. We can press at high level, but we need this interface totally clean. Then if we have a coated surface, this possibility doesn't match very nice with the final result. Because if we have a coating here, this coating is going to disappear and diffuses into the pool that is formed in this located area. In case of sinter bonding, is very attractive because we can put together different material, a wrought steel and a green press material, and together we can form the final structure. Very attractive in that case. In the case of brazing, brazing is I think is the most frequent joining method that is chosen for PM production, because you put it together, the pieces that you want to join, and the filler metal in the same furnace. Then the filler metal should be compatible with the atmosphere in your furnace and with the chemistry of your component. And it's not so easy, because maybe you can think that you need a filler material specifically designed for every kind of composition that you can find in your PM materials, steels, or in Cornell-based material, whatever. It's very difficult to find this alloy design for that option. And normally in the market you can find 3-2 solution able for sinter brazing. But it's possible to design it. It's possible to find some more compatible bracelet depending on your system. And there is a lot of work that can be made here. You have to take care also, if you are going to do the join by brazing, you have to take care about the density. Normally the brazier is going to be done during the sintering, not after sintering. But during the sintering you need a certain level of porosity, because this is how can be placed like that, the brazier, or can be put it like a paint, okay? And then during the sintering it's going to melt, and by infiltration is going to infiltrate the open porosity of both components and form the final joint. What happens if you put too much, or if the dissolution with the component is very high? Then you are going to affect the final microstructure, or you are going to introduce a very big distortion of your component. Then it's so critical how this material melts and how this material is able to move into the pore skeleton of your component. Let me show you how it looks like brace joint. This is with 2 PM materials. This is with a PM par and a rose steel after stamping. And here you can see how the brace penetrates into the PM par, but do not penetrate into the stamping materials. In that case, look this distance. This is where is placed the brazier, and look this distance. This distance means that was able to penetrate for the, into the porosity in that amount of material. It's very important to control the reactivity, the degree of dissolution between the brazier and the material that we are using in that case. To start with the second level of secondary operation, they are that related with the final microstructure. It's impossible to give you an extremely precise idea about the huge volume of heat treatment that we can find, or we can need it. I center this one in PM steels, low alloy steels. Of course, there is a lot of another treatment that we can apply. For instance, if we are working with aluminum, Inconel, super cobalt alloys materials, but I have to select some of them. In case that you needed more information for other family of material, please contact me after this summer school and I can give you more information. Well, heat treatment are used to tailor faces. Once we have the initial composition, maybe we need to tailor the different microstructure, the different microconstituents that we have in the final component. Then this heat treatment can be done during the cooling of our sintering processes or after the sintering processes. If I am a PM part producer, I will like to make the treatment during the cooling, because I do not increase the number of steps in my PM route. But in some cases, it's impossible. In case of the steel, depends on the hardenability of our system. And we are going to discuss this hardenability. What are the special features for PM steel? The alloying distribution, is it heterogeneous microstructure or unhomogeneous microstructure? The base powder is pre-alloy, is pre-diffuse. I am expected the same degree of alloying in the whole microstructure or depend the area that I selected. And also the porosity. In equilibrium condition, we know exactly what we can expect depending on the carbon level on the final microstructure. Then we took the phase diagram and we are very happy because we can understand what happened at the end of the process. The final microstructure in a wrought steel, in an anneal wrought steel, looks like this. In our case, it's quite similar, but with some pores inside. Well, this kind of microstructure is the right one if you want to machine the component. It's the softer, then the tool life will be increased. It's more easy to machining than any other. Then if you need to include a machining operation in your PM route, look for this kind of possibility of the microstructure. Do not machine in a component, being by night, fully martensite, or wherever. Try to look for this microstructure. But in heat treatment, the equilibrium conditions are out of scope, and we need this kind of diagrams that represent the evolution of the microstructure in an isothermal treatment or in a continuous treatment with a continuous cooling. This kind of diagram give us the beginning, where it starts the beginning of the transformation of the austenite and when it's going to end. And in the middle, we know more or less the amount of microconstituents that we are promoting by the time that we are at this level of temperature. Hardenability can be defined considering how easy it is to form martensite in our material. We are going to austenitize an steel and then cool it, and then we can see how difficult it is to achieve a final level of martensite. Depends on the alloying elements, of course. If we have a plain carbon steel, it's impossible to achieve a martensitic structure in any case. Okay, we need to increase the alloying element contents. And also, we need to know exactly the porosity of our material. Let me show you how it works, the alloying elements in the steel. This is how they can modify the eutectic temperature, the eutectoide temperature, and also the carbon content that when it's happening this eutectoide temperature. Some of them decrease the temperature, and some of them increase it. This is the gamma stabilizer, this is the alpha stabilizer element. All of them decreases the martensitic start temperature, all of them decreases the martensitic finish temperature, and affect the response of the cooling of the material. Let me show you the difference between the gamma stabilizer and the alpha stabilizer. This is the critical temperature, the upper critical temperature. If we consider a gamma stabilizer, then the critical temperature is going to decrease because the region of the austenite is bigger. It's just the opposite that is happening when we consider the chromium one. The chromium tends to increase or tends to decrease the region where austenite is stable, and also delay the transformation of perlite. That's the reason why here we only have this curve, and here we divide into regions: the perlite transformation, the vinite transformation. Here is delayed the formation of cementine in this kind of structure that we have in the perlite system. But look how the curves are shifted into your right when we increase the amount of manganese and when we increase the amount of chromium. If we didn't put chromium or manganese, curves are more in that sense, move in that sense, that was impossible to achieve the martensitic microstructure. Okay? Then we needed these alloying elements. Another way to understand the hardenability is like it's wrote here. I like it more than the other. The greater the hardenability, the slower the cooling rate needed to produce a martensitic microstructure. Because heat treatment at the end means distortion. And then if my material has a certain level of hardenability, the environment that I need to cool down the material is not as severe as if my material do not have this hardenability level. And then the level of distortion is relatively lower. I tried to put a video in my presentation, but I always fail. Then I invite you to type in Google water quenching distortion. And in video, it's going to appear how when a bar is cooled down in water, we are going to lose totally the geometry of the bar. It's just in the first 2 seconds, okay? You have the bar, and then suddenly, distortion due to quenching. You have to type, water quenching distortion is the first option. Then once you see this, you understand why you need to increase the alloying content, because you don't want this kind of distortion. That video, did you achieve that video? In the first seconds, then a perfect bar is going to make like a nice curve at the end. Yes? What it could happen if you put a gear in water quenching? Can you imagine? Your effort for the die to press perfect, the tolerance after blah, 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 totally destroy. Yes? This is what happened with the video, okay? I tried too many times, but it was impossible. Okay, just to finish, I would like to make some brief comments about the heat treatment that we can find. The bulk heat treatment, annealing normalized through hardening, stress relieving, etc., and some of the case hardening. These are the normal heat treatment that we have in conventional steel. The same is in our cases. Normally, we can choose the through hardening when we heat up to a certain level of temperature in the austenized region, then rapidly quench, and then make some slow tempering and stress relieving. A stress relief annealing is also needed after machining, for instance, or is also needed after some chemical treatment at the surface that can promote some distortion, or when you need to relieve some stresses that are in the component. When we are looking for the case hardening, we need to detect how is the depth of our treatment. In that case, we can make a profile of microindentation in our component to verify how deep was this treatment. What are the different possibilities for modifying the surface chemistry? We can see the carburizing, carbonitriding, nitriding, or nitrocarburizing our component. In case of carburizing, take into account the open porosity and the amount and the initial amount of carbon that you have in your component. Because if it's higher than 0.5 of carbon, has no sense to enrich the surface with more carbon. Okay? And if the open porosity is very high, then you are going to make a completely carburizing of the section of your component. Then you have to take into account these two critical aspects. In every case, you need, in case of carburizing, you need to quench and tempering. Quench and tempering, remember the part that you have seen cool down in water? Distortion, okay? But carburizing is selected in too many occasions because it's very versatile for PM materials. Another option is, why not to go to surface treatment without this level of temperature? Well, this happens depending on the porosity. High level of density, high level of porosity. Look how is modified the depth of the case hardening in that case. Well, I said, what happens if I enrich the surface with other elements that is not carbon? Nitrogen, nitridine, nitrocarburizing. In that case, the temperature is just 500, 600 degrees. The level of distortion here is much less than in case of carburizing. That is very attractive. And then why do not go to nitridine instead of carburizing? In case of nitridine, we need some elements that like to form nitrides. Then not all the scope of alloying steel are able to have this kind of treatments. We need to choose perfectly the composition of our component. There is another possibility, better than gas nitridine, is plasma nitridine. Plasma nitridine works better, makes less distortion, controls much more the depth of the treatment, but it's more expensive. Maybe it's relatively longer, the process that you needed to succeed with this treatment, and then also increase the cost. But it's one of the best options because offer the best results for the nitriding processes. Steam treatment is a very, I think, old-fashioned treatment, but that works because promote an oxide layer that covers perfectly our surface, works perfectly for wear resistance, do not decrease the resistance of the component, can feel the porosity, the open porosity. Look here, this is the coating, the oxide layer, and how the open porosity is also covered by this very well adhered oxide layer, and works very nice instead if we are thinking in wear resistance. This is the wear rate of the sintering component and the steam treated component. We can also give some others like infiltration, impregnation, and so on, but this was discussed in different moments during the school. But no one has told you that at the end, you have to clean the component. And this is very critical if you are a part producer or if you are the customer. Because if you are a part producer, you are going to offer these two options. They are less expensive, more easy, is clean enough, because cleanliness was defined to avoid any kind of chip contamination during machining. But at the end, the customers want a more cleaning component. And then all of them likes ultrasound cleaning. Very expensive. But this is the market law. You can offer something, but at the end, the customer needs or wants a special one. But this step is need to include in all the PM route that you can design. At the end, you have to clean the component. At the end, you have to clean the surface for a better performance. Thank you very much. Please take my email.